the next component for building a digital circuit is the delay element. This delay element can be implemented in three different ways. One is by using a pass transistor and a CMOS inverter, and the second method is by using clocked CMOS logic. It can be referred as C squared MOS logic in short. And the third method is by using true single phase clock, TSPC. Coming to the simple delay element by using a pass transistor and CMOS inverter. This circuit represents a delay element by using a pass transistor and a CMOS inverter, where the pair M1 and U1 forms the master stage and M2 and U2 forms slave stage. And it could be observed that M1 is controlled by clock complement and M2 is controlled by clock, and thus this delay element uses non-overlapping clock signal, clock and clock bar, where clock is M2 is controlled by clock and M1 is controlled by clock bar. This circuit represents a transistor level implementation of the delay elements, where this forms the master state and this forms the slave stage, and C1 is the output of the master stage and C out is the output of a slave state. When clock is 1, when clock is logic 1, M2 will be in on condition and M1 will act as a open circuit, so there will be no connection for input to the C1 stage. When clock is 1, slave will be in active state and master will be in inactive state. Thus, the voltage across the C1 will be passed on to the slave inverter, and C out will obtain the voltage from slave inverter. On the other hand, when clock is made 0, clock bar will becomes 1, so M1 will be in on condition and M2 acts as an open circuit now. So there will be no connection from input to the output when clock is made 0. When clock is 0, clock bar will be 1, so this will be in on condition. Thus C1 will obtains the voltage from the input value during clock is equivalent to 0. So this is the circuit which represents a positive edge triggered delay element, where in the waveform you can observe that this is the input signal, the second signal is the clock signal, the third signal is the master output or the voltage across the C1 capacitor, and the fourth signal represents the output signal. And it could be observed that when clock is logic 0, master will be in active state. When clock is 1, slave is in active condition, and whenever the slave is in active mode, the output represents the delayed version of the input. Observe here, you could observe here, during this phase slave is active, so output is nothing but the delayed version of the input value. In the same way, the delay element can be implemented by using negative edge triggered delay element, where the control should be swapped now. If you apply clock here and clock bar here, that will represent a negative edge triggered delay element. The second technique for implementing the delay element is by using C squared MOS logic, that is clocked CMOS logic. The general skeleton for C squared MOS logic includes PMOS logic, NMOS logic. Between this PMOS logic and NMOS logic, one PMOS and one NMOS should be connected in series, which are controlled by non-overlapping clock phases, again clock and clock complement. Here you people will be getting the output, and to the PMOS logic and the NMOS logic, input will be applied. This is the general skeleton of a C squared MOS logic. This circuit represents a delay element by using clocked CMOS logic or C squared MOS logic, where it includes two tri-state inverters. This is a master state tri-state inverter and this is a slave stage tri-state inverter, where this MOS FET MP is referred as a reset MOS FET. If reset bar is equivalent to 0, then this MOS FET will be in on condition, which connects Vx to VDD. Thus the output will be reset to 0 whenever the reset complement is 0, and hence this MOS FET MP is referred as a reset MOS FET. This is again a positive edge triggered delay element because M3 and M4 are controlled by clock complement and clock here. In the same way, M7 and M8 are controlled by clock and clock complement. When clock is made 1. When clock is made 1, M7 and M8 will be in on state. On the other hand, when clock is made 1, the M3 and M4 acts as a open circuit. It acts as an open circuit, so there is no connectivity between the node X and input, wherein since these two MOSFETs are in closed state, whatever the voltage is available here will be transferred to the input of this inverter, and hence output will always be the inverted version of Vx, which in turn is equivalent to V input when clock is equivalent to 1. On the other hand, when the clock is made 0, clock will be 0, clock bar will be 1. Now these two MOSFETs will be in off state, wherein when clock is made 0, M4 and M3 will be in on state, so that Vx will obtain the voltage from input. Now Vx will always represent input complement. Then coming to the third way of implementing a delay element, which is by using true single phase clock. In the first and second type, both clock and clock complementary bar, clock and clock bar signal will be used for controlling or for developing the delay elements, wherein in the third method only a single phase clock will be used. So this circuit represents a delay element using true single phase clock, where you can observe that this is the first stage inverter, which is nothing but a PMOS dynamic inverter, wherein the second stage is also an inverter which represents an NMOS dynamic inverter. This is also an inverter state where the output of the second stage inverter will be given as a gate control of the third one, and M8 will accept the clock as a control. When clock is 0, for this particular circuit, when clock is made 0, this will be in on condition, so that D will be, this will be in on condition. So if D is equivalent to 0, this will be in on condition, so X will always takes the value D bar. Since this is an inverter state, the output is always an inverted version of the input. When clock is made 0, this will be in on condition, so that X value will be D bar. In the second inverter stage, since clock is 0, this is in on condition, this is in off condition. Depending on the value of X here, this inverter will be in the pre-charging phase, because when clock is 0, this will be in on condition and this will be in off condition. So Y will be always connected to VDD, and this is referred as a pre-charging phase. Then coming to the third stage, since I have considered clock value as 0 here, this will be in off condition. Since Y value is VDD, this will also be in off condition, so the third stage will be in hold state. On the other hand, when the clock is made 1, when the clock value is high, assume that I am supplying logic 1 value as the input D here. So at this point, inverted version of the D will be obtained, so this will be 0. Coming to this dynamic inverter state, since clock is 1, this will be in on condition, this will be in off condition, and this inverter state operates in evaluation mode now. Since this is 0, output Y will always be 1, because previous value is also logic 1. So depending on the value of the input, Y will be either connected to the ground point or it will be retained in the previous state, which is nothing but logic 1. If X is 0, Y will be at logic 1 itself. Now clock is 1 means M8 will be in on condition, Y is 1, which makes M7 to be in on condition, and this will be in off condition. So these two are in on condition, so Q bar will be logic 0, which has been passed through an inverter to generate the output Q, whose value is always equivalent to the input value. You can observe here. If the value of the input is assumed to be 0, then X, which is equivalent to D complement, always the value of X will be logic 1. Since this second stage is in evaluation mode, since this is logic 1, this will also be in on condition, so Y will be connected to the VSS, so Y value will be logic 0, which makes M8 and M9 to be in on condition, so Q bar will be logic high and Q will be logic 0, which is again equivalent to the input which has been applied when clock is equivalent to 1.